Section 1.6, page 3. So now let's talk about techniques for solving limits of a rational function, which a rational function is just a fraction. So we're going to divide the numerator and the denominator by the highest powered variable in the denominator. So your variable may not always be x. Going back to the pizza pie example, that basically the bigger the number you're dividing 1 by, or really any number, this could be 17, and that's not going to change it. We're going to end up with something so small that we're going to answer 0 for anything divided by infinity or negative infinity. So let's look at this first example. We're asked to evaluate a function here, and I need to go down to the denominator, and I need to find the highest exponent variable. So in this case, the highest power of x in the denominator is x to the fourth, which is what I want to divide each term by. So I take the original 2 plus x squared and individually divide each, I said x squared, it was x to the sixth, divide each term by x to the fourth. Again, I'm going to take the binomial in the denominator and individually divide each term by x to the fourth. Now, next step, I need to simplify where I can. 2 over x to the fourth does not simplify at all, but using the simplification algebra technique of numerator exponents subtracting denominator exponents, I can take this 6 minus 4 and just end up with an x squared, which is either in the numerator or by itself. Here, don't forget that when I cancel the 2x to the fourths, I have 1, right? I was really doing x to the fourth divided by x to the fourth, and anything divided by itself is 1. Now, careful here, if I was to subtract a 4 exponent, I'd get negative 1. So I want that negative 1 to go into the denominator. Or you could just think there were 4 on the bottom, there were more in the denominator, so these 3 will knock out 3 of those, just leaving me 1 left. Notice limit is still in front of the simplified equation. But now, limit is gone because we have plugged infinity in wherever the x was. So I want to see the infinity plugged in, and then using the fact that any number over infinity or negative infinity is 0, we can turn this term into 0. But for infinity squared, we're just going to write infinity because that's not an actual number. We had a 1 here, so that didn't change. But again, I'm back to having a number divided by infinity, even though it's a 3, so I get to write a 0. Now I will go ahead and simplify to get infinity in my numerator, 1 in my denominator, and infinity divided by 1 is infinity, the answer to this question. Next question. I'm looking at the denominator only. I see an x squared, so that's my highest exponent variable, and I need to divide numerator and denominator by x squared, but maybe you want to write it as 1 over x squared. It's the same thing, but for some people visually that helps them remember that they need to put it under each of those terms. I still have the limit as I'm dividing everybody by the same term, simplifying by canceling this x with one of these to have only a single x in the denominator, nothing to simplify on the top right term. These cancel to give me a 1, and this x cancels with one of these to give me just a single x in the denominator. I still have limit in front of the equation because I still have x's here. But now that this infinity is going into the x's, there is no limit in front. I've placed infinity in every spot I had an x and simplified. Any number over infinity is 0, even if it's a 9 over infinity. 1 does not change, but 7 over infinity becomes 0. And so 0 over 1 equals 0. Remember, it's only a number over 0 that does not exist. This one exists. And one last example. I start off just fine. I find my largest variable exponent in the denominator of x squared. I'm going to divide the numerator and denominator by x squared, keeping limit in front. It looks good until I get here when I go to simplify. What happens is this square root is causing me a problem. I cannot divide this x squared under the individual terms as is because it's not in a radical. Remember, the rule is if you have a radical divided by the same radical, then you can go ahead and do the division on the inside, right? A square root can't divide by a cubed root, but fifth root divided by fifth root, then you can go ahead and divide the insides. So what happens is I need this x squared, I need it to be in a radical. Well, here's the interesting thing. X squared comes from the square root of x to the fourth. This is a true statement. So instead, if I had had x to the fourth in the denominator, because these are both radicals, then I could have an individual fraction. And then, of course, because this is a monomial, I can divide each term separately by that monomial. So that's what we're going to do. We can kind of just jump to putting that x to the fourth inside the radical, but notice it's x squared everywhere else. And again, we still have our limit out front. So now I can simplify. This x will cancel with one of these to give me a single x. These cancel, and instead of writing 1, it's 36 times 1, which is just 36. And this cancels, leaving me 3 x's in the denominator. Coming over here, well, actually, I guess we just rewrote it, right? So now I'm going to simplify. These cancel, but they don't give me a 1. They give me a 3, and there was nothing to simplify in the last term. Still have limit in front of my function. But I'm ready to use up that limit. I'm ready to take this infinity and put it where all the x's were so I can get rid of the limit. As you see here, anything over infinity is 0. Anything over infinity is 0. Anything over infinity is 0. So really, I'm just looking at the square root of 36 over 3. And because the square root of 36 is 6, 6 divided by 3